Welcome. So we're going to see whether the jump-in road trip can actually happen. Like, are they going to make it over the bridge? So we're going to start with a little sketch. So we've got, okay, and it's going to follow a parabolic trajectory. And the question is, will it make it? Okay. So what do we know about this problem? All right. Look, I made the sketch right here when I shouldn't have. Haha. Okay, so again, it's really important to keep X and Y completely separate because the rules for X and Y are different. Okay, so first of all, so what do we know about the problem? So we know that the car is traveling at, hopefully, this diagonal velocity is, they said they're going to try to go 60 miles per hour. I did the math there, and 60 miles per hour is roughly 25 meters per second. Okay. Now, in the video, they talked about being a 30-degree angle. And fun fact, when we're actually looking at angles that we actually have to traverse, we are grossly wrong. All right. So I put a protractor up on the screen, and though he said it was 30 degrees, the actual angle is only 10 degrees. Okay. For your, just for like comparison, Buffalo Hill, 11 degrees. Stairs, which you might think are 45 degrees, 33 degrees is standard. So if we actually have to traverse a slope, we think it's much, much steeper than it is. All right. So I think a double black diamond is like, I can't remember, it's 20 or 40 degrees. Yeah, I have to look that up. All right. So neither of these are X and Y. They cannot go here. All right. So what you need to do is you need to separate the things into components. Okay. One sec. Okay. So I'm going to separate this into X and Y components, which is why we did vectors at the beginning of the year. All right. So there's an X component that never changes, and then there's an initial Y component. All right. In order to figure out what those are, we need formulas from our reference tables. All right. So if we want to know the Vx, the one that never changes, that is the X component. And if you remember on your reference tables, the X component is whatever the diagonal vector is times the cosine of theta. All right. So Vx is going to be 25 meters per second times the cosine of 10 degrees. And the VIY, similarly, is going to be 25 meters per second times the sine of 10 degrees. Okay, give me a second while I figure out what those are. Okay, so I did the math, make sure you're in degrees, and I got that the X component is 24, which makes sense because it's pretty close to horizontal, and the Y is 4.3. All right, that's what these things are. Never put these diagonal pieces of information into your chart. Okay, now, what else do we know? Everything else is hidden. So we know that acceleration due to gravity near the Earth is negative 9.81. And again, I'm going to make down my negative direction. Okay. And then we know one other piece of hidden information, which is that at the top, the VFY equals 0. So the velocity at the top, and you decide when final is, and I'm going to say that, is VFY. Is 0. These pieces are at the top. This is true for pretty much every projectile problem that we have in this class. We need to move it down. Okay. Now we have enough information to find time, because remember, the first thing you want to do is find time. So again, hidden information here is that Vy is going to be 0 at the top, and acceleration is negative 9.81 meters per second squared. All right. Okay. Now, we need to pick a formula that has all of these things in it and nothing else, and we want to find time. Okay. So we have 1, 2, 3 pieces of information, and we are looking for time because that's the thing that unites the X and the Y. So what we want then is this formula here. VF equals VI plus AT. So, whoop. VF equals VI plus AT. And again, be really careful about keeping X and Y separate. All right. So, 0 equals VIY is 4.34. Don't put that 25 in there. Plus a negative 9.81 times t. We're going to do algebra and solve for t. So we got to subtract 4.3 from both sides. So negative 4.34, I'm dropping units, equals negative 9.81 t. So when I do the math there, I get that t equals 0.44. Now, this is the time up to the top. Okay. This is not the total time it's in the air. So this is one of the problems that makes this hard. So in order to find total time, you got to double that. And I get time is 0.88 seconds. Now, what I can do now is come over here and actually find the dx. So the formula we always use on the horizontal side, because velocity doesn't change, is v equals v over t. All right, and again, either be really careful about keeping x and y separate or put them in separately. And I'm going to rearrange this, and I get dx equals vxt. So if I then plug in, I get that dx equals, again, the vx, don't put the 25 in there, put in the x component. So 24.6 meters per second times the 0.88 seconds. And when I do that, I get that the distance traveled is about 22 meters. So, keep in mind that if you want to know how far that really is, that is dx, if I multiply that by 3.29, that'll give me the feet. So this is actually equal to 71.6 feet. Okay, so, sorry, I moved all this down and you can't see. All right, so did they make the jump? Well, if the jump was less than 71 feet, yes, they did. If that number seems incredibly large to you, it's because you're thinking about cars jumping. If you thought about shooting a rocket at 60 miles an hour at an angle of 10 degrees, you would expect it to go 71 feet. That's reasonable. It's just you're thinking car, right? Okay. So I think we can safely say they made the jump.